Dear students, Assalamu alaikum. Today I am again with you people, and today I have chosen two small topics. One is we will try to find out the magnetic dipole moment of a revolving electron, the electron which revolves around the atom, and then another our other topic will be comparison of magnet, Bohr magnet, and solenoid. So let us first take the first part of this topic. That is the magnetic dipole moment of a revolving electron atom as a magnetic dipole. We know that a current loop behaves as a magnetic dipole and its magnetic dipole moment M is given by M is equal to IA. This we have already discussed in our early classes, and in our last class we also discussed it, magnetic dipole moment of a current loop. So we know that the magnetic dipole moment of a current loop is given by M is equal to IA, where I is the current flowing through the loop and A is the area of the loop. Now, in an atom, what happens? The electrons revolve around the nucleus. We all know that, and the circular orbits of electrons may be considered. We can treat them as the small current loops, and we will expect that they possess magnetic dipole moment M. Because when a charge flows in a circular loop, it, it is the electron which flows around the loop. Similarly, it is the electron which revolves around the nucleus. So, by analog, we can expect that the electron will also constitute a current the same way as it forms the current in an current loop. So, when an electron revolves around the nucleus, we expect that the electron will have a magnetic dipole moment M. Now, let us consider an electron of charge E and mass M revolving around the nucleus with velocity V as shown in figure. As you can see from the figure, we have an electron of charge E. It is moving around the nucleus in anti-clockwise direction, as you can see, as I have shown it, and it is moving with a linear velocity v, though it is moving with an angular velocity, and we know that linear velocity is equal to omega r, the relation between angular velocity and linear velocity. So v is the velocity of the electron, linear velocity of the electron is the charge of an electron, and m is the mass of the electron. So the electron is moving in anti-clockwise direction, so the current will also be moving in the anti-clockwise direction. Let r is the radius of the orbit of the electron. Then the angular momentum of the electron is given by L is equal to mvr. Actually, the relation between angular momentum and linear momentum is L is equal to p into r. Remember this thing. Angular momentum is equal to linear momentum into r. Angular velocity is equal to linear velocity into r. Similarly, angular acceleration is equal to linear velocity into r. So angular momentum is denoted by capital L, and so L will be actually equal to, so actually what this L will be equal to P into R. Sorry, it is small r. Remember this, it is small r here. So, but we know that linear momentum P is equal to mass into velocity, that is mv. So when we substitute for P mv, we get L is equal to mv r. So as I have written already it here, L is equal to P into R, that is mv r. L is directed perpendicular to the orbit of the electron in upward direction. If T is the time period of the electron, then I will be equal to E upon capital T. Here T is the time period, T it is actually capital T, it is the correction. it is capital T. T is the time period of the electron, then I will be equal to E by T, because we know that current I is equal to charge by time. So this implies I is equal to E by T, or I into T is equal to E. Now we know that velocity is equal to distance by time. This implies V will be equal to 2 pi r by capital T, because the distance traveled by the electron in a circular orbit is equal to the circumference of the circular orbit, that's 2 pi r. So V is equal to actually S by T, but S here it is circumference of the circular orbit, that is 2 pi r. So V will be equal to 2 pi r by T, or T will be equal to 2 pi r by V. This implies when we substitute in equation first the value of T, we get I into 2 pi r by V is equal to E, which implies I is equal to EV by 2 pi r. Let us denote this equation by 2. Now magnetic dipole moment of the atom is given by M is equal to I into A. Now we substitute the value of I and the value of A. So value of I we have calculated in equation 2, that is EV by 2 pi r into is the area of the a circular orbit of the electron, that is pi r square. So pi and pi will cancel, or 1 r and 1 r will cancel. Ultimately we will get M is equal to EVR by 2 into here M by M. I have multiplied and divided whatever remains in this equation. We multiply it and divide it by M. So it will be M will be equal to EMVR by 2M. Now L is equal to MVR. We are already derived it. L is equal to MVR, which implies M will be equal to EL by 2M, because MVR is equal to L. So magnitude dipole moment M will be equal to EL by 2M. Now according to Bohr's theory, angular momentum of an electron in a stationary orbit can have only those values which are integral multiple of h by 2 pi. This is one of the Bohr's postulates. According to the postulates of Bohr's theory, the angular momentum of an electron in a stationary orbit in one orbit can have only those values which are integral multiple of h by 2 pi. So this implies L will be equal to nh by 2 pi, while n is equal to 1, 2, 3, so on. This implies M is equal to E by 2M into nh by 2 pi. We substitute the value of L here. So M becomes equal to E by 2M into nh by 2 pi. This ultimately gives us M is equal to NEH by 4 pi M. And this is the magnetic moment of the electron due to its orbital motion. Now let us define Bohr magnetron. The magnetic dipole moment of an electron due to its orbital motion in the first orbit, that is n is equal to 1 of hydrogen atom, is called Bohr magneton. So what is Bohr magneton? It is the magnetic dipole moment. It is a magnetic dipole moment of an electron due to its orbital motion in the first orbit, that is n is equal to 1 of which atom? Hydrogen atom, is called Bohr magneton. So what will be Bohr magneton? We have to substitute in the above equation. M is equal to NEH by 4 pi M. We have to substitute for N1, and we know the charge of electron is 1.6 into 10 raised to minus 19. Then Planck's constant H, that is 6.62 into 10 raised to minus 34, divided by 4 into, for pi we write 3.14, and for M mass of an electron, that is 9.1 into 10 raised to minus 31. And when we multiply and divide, we get M is equal to 9.27 into 10 raised to minus 24 ampere meter square. So this is the Bohr magnetron. If anybody asks you What is Bohr magneton? So it is numerically equal to 9.27 into 10 raised to power minus 24 ampere meter square, and you can calculate it yourself by substituting the values of different terms in the above equation. Now, as I told you, our other topic is comparison of Bohr magnet and solenoid. That is, Bohr magnet acts as an equivalent solenoid, or other words, a solenoid acts as an equivalent to Bohr magnet. They have many similarities between them. That is why solenoid is acts as a Bohr magnet, and Bohr magnet acts as a solenoid. The Bohr magnet and the solenoid have similar field lines pattern. Similar field lines pattern. The field lines of Bohr magnet are shown in fig. Uh, I can show you later on. Fig 1, and the field lines of solenoid are shown in fig 2. The field lines inside the solenoid and Bohr magnet are shown close because magnetic field is stronger inside the Bohr magnet as well as inside the solenoid. The field lines are drawn on a sheet of paper by using a compass needle. We put a Bohr magnet on a sheet of paper and then bring a compass needle close to it and then take it from the north pole of the Bohr magnet to the south pole of the Bohr magnet. The path which the magnetic needle follows becomes the magnetic line of force or magnetic field line. The magnetic field lines for a Bohr magnet and solenoid are closed curves, as you see from the fig, uh, first and fig second. This is the fig first. This is fig first, and here it is fig second. Fig first shows us the magnetic lines of force of the Bohr magnet or magnetic field lines of the Bohr magnet, and fig second shows us the magnetic lines or magnetic field lines of a solenoid. You can also see the similarity. Now, what is the north pole of the solenoid? That is given by clock rule. If the direction in the phase, as in the last lecture I told you, is anti-clockwise, if the direction of the current where the in one of the faces of the solenoid is in anti-clockwise direction, then that face behaves as a north pole and other face behaves as a south pole. So here you can see that the right face of the solenoid acts as a north pole, and the left face of the solenoid acts as a south pole. So field lines are almost similar. You can see from the two figures. So the two figures clearly demonstrate that solenoid behaves like a Bohr magnet. It has a north pole like a Bohr magnet. It has also a north pole and south pole. The solenoid has also a north pole and south pole, and we can determine its north pole and south pole by clock rule. Looking at the phase, if the current in it is the anti-clockwise sense, then the phase has the north polarity. That is, that phase acts as a north pole, and if the current in it is in the clockwise sense, then the phase has south polarity. So you can see the magnetic lines of force at the ends of the Bohr magnet and of the solenoid are dense. Uh, they are very close to each other. Inside the solenoid, you can see from the fig, and inside the Bohr magnet, they are very close and they are parallel. They are almost, so the field inside the solenoid and inside the Bohr magnet is uniform. Outside the solenoid, the field lines start from north pole to south pole, and inside the solenoid, they start from south pole to north pole. And you can see they are in both the cases they are closed curves in Bohr magnet as well as in solenoid. So when we compare this Bohr magnet with the solenoid, it is almost equivalent to the solenoid is almost equivalent to the Bohr magnet. It has all the similarities, it has all the properties which the Bohr magnet has. The magnetic moment of the Bohr magnet is m is equal to m into 12, and that of solenoid is m is equal to I into A. So both the solenoid as well as the Bohr magnet have got the magnetic dipole moment. In Bohr magnet, it is equal to magnetic strength and the length between the two poles, and in solenoid, it is equal to the product of the current and the cross section area of the solenoid. So thank you. See you inshallah in the next class. And as you can see from the picture, our next class will be Earth's magnetism or Earth's magnetic field. Thank you.